Let's say we want to find the length of the curve y equals f of x from A to B. Well, we can think of this as we know the length of a straight line that we can use to approximate this length. So if we draw a triangle, it's a right triangle, and we're trying to find the sides, we know that this side we can call side A, and we'll call this side side B. So we know by the Pythagorean theorem that a squared plus b squared equals c squared. So if we know this length A and this height B, we can find the length of that straight line. And we can extend this idea to making many straight line segments to approximate our curve. We'll find that as we have more and more lines to approximate our curve, we'll get a better and better approximation for our curve. So now, if we have one slice is drawn with the straight line, here's our actual curve, and we have our right triangle. So this is our change in x, this is our change in y, and this is going to be our change in s. So by the Pythagorean theorem, we have that the change in x squared plus the change in y squared equals the change in s squared. So that means that the change in s is equal to the square root of the change in x squared plus the change in y squared, and we would want to add up all the approximate slice lengths to get an approximation for the total arc length of our curve L. So that means that our length is approximated by the sum of all of our square root of change in x squared plus change in y squared. So if we have a curve, we're adding up all of our line segments that we use to approximate the length of the curve. So now we have the square root of change in x squared plus change in y squared. Let's rewrite this so we're all in terms of x. So this is equal to, if we pull out a change in x squared, then we can rewrite this as the change in x squared times 1 plus the change in y squared over the change in x squared. If we think about this, if we multiply this back in, then we'll get the change in x squared, and the change in x squared times the change in y squared over the change in x squared will give us back the change in y squared. We can separate these square roots, so we have the square root of the change in x squared times the square root of 1 plus the change in y over the change in x quantity squared. And the square root of something squared is just so we'll have just delta x times the square root of 1 plus change in y over the change in x quantity squared. And we can use the mean value theorem to rewrite the change in y over the change in x as f prime of x star for some x star in the sum interval. So we have the change in x times 1 plus f prime of x star squared. We should also note that as our change in x goes to infinity, our change in y over our change in x goes to f prime of x if f is differentiable. So now we say that L is equal to the sum of the square root of 1 plus f prime of x quantity squared times the change in x. So if we take the limit as our number of subintervals goes to infinity, then we have that the length equals the integral from a to b of the square root of 1 plus f prime of x squared dx. Or we can rewrite this as the integral from a to b of the square root of 1 plus dy over dx squared dx. So formally, we say that the length for y equals f of x is that f of a continuous first derivative on the closed interval a to b. The length of the curve from the point a, f of a, to b, f of b is the integral from a to b of the square root of 1 plus f prime of x squared dx.